folks. Today we're going to learn how to factor special products. We've spent the last couple lessons factoring just by listing all the possible factors of the A value and the C value and kind of seeing what works. However, before we learned how to factor, we did learn a couple special patterns. We learned the difference of two square patterns and the perfect square trinomial pattern. And if you look out for these when you are factoring, especially if you have an A value in front of your squared term here, this can help the process go faster if you can recognize these special patterns and factor more quickly. So let's remind ourselves what these special patterns are. First, we're going to look at a difference of two squares. And when we have a squared value minus a square value, the bases of those squares can be used to create a multiplication pattern with two polynomials, a plus b, a times a minus b. So let's look at an example of that. If I see that I've got my first term, my variable squared term is a square number, and my last term of the polynomial is a square number, that's when I should start looking out for some of these special products. Here, I only have two terms. I don't have three terms. So automatically that should make me think of the difference of two squares pattern because all I have are the two squares. So here, what I have is my a squared value is x squared, and my b squared value is 5 squared. So you kind of need to take the square root of the first term and the square root of the last term. And now I can write this pattern as being a plus b times a minus b. That's x plus 5, the quantity, times x minus 5, the quantity. And that's how you factor the difference of two squares, so long as you've recognized the pattern. Let's look at a more complicated example. Here, I don't have a variable just by itself. My variable is multiplied by a coefficient, but my coefficient is also a square number. So if I think of this term as being a squared, if I take the square root of 4z squared, I am left with 2z. So 2z, when I square it, gives me 4 squared. My b value is a squared number. 1 is just 1 squared. So my b value is 1. And so if I want to write this as a difference of squares pattern in terms of a multiplication problem, that is 2z plus 1 times 2z minus 1. And that's how you use the difference of two square patterns to factor a polynomial. Notice here we did have a coefficient in front, a leading coefficient on our x squared or z squared term here. Those were harder to factor sometimes. In the previous section, those were more complicated to factor where you needed to list a whole lot of factors for the a value and the c value. But if you can recognize this special pattern, then you don't have to go through that process of making a full list of factors because you see what your end value is automatically. We don't have to apply this special rule to just polynomials. We can apply them to values without variables. So if we look at this math problem, 54 squared minus 48 squared, both of those square values are very large numbers, and I don't particularly feel like attempting those in my head. But we can simplify this problem by writing it as the difference of two squares. This is my a value, 54, and my b value is 48. So if I rephrased this math problem as 54 plus 48 times 54 minus 48, these are now math problems that I can do in my head. 54 plus 48 is 102, and 54 minus 48 is 6. So if I just multiply those values together, I get 612. And those were math problems I was able to do in my head, whereas I don't really feel like squaring 54 in my head. Let's look at another example here. This time we're going to be factoring perfect square trinomials. And there are two perfect square trinomial patterns depending on whether your second term is positive or negative. But in both cases, the first term is a square value, and the final term is a square value. And then the middle term is 2 times the base A times the base B. So let's try to look at how to spot this. Here I'm given a trinomial. I'm going to look at that first term and see if it's a perfect square. It is. It's n squared. So this is potentially my A value for this factoring perfect square trinomials. I look at the last term. Is it a perfect square? Yes, it is. 4 squared is 16. So this is potentially my B value. What I need to do now is look at the center term and see if it is 2 times A times B. Is it 2 times my A value, which is n, times my B value, which is 4? Well, 2 times 4 times n is 8n. And so, yes, this center value does follow the 2AB pattern. Therefore, this is a perfect square trinomial. And so to factor it, I write it as a perfect square. My A value is n, my B value is 4, and I write it as, and I square it. Let's look at a little trickier example just because we've got a coefficient here, a leading coefficient on our first term. But that leading coefficient is also a square number. So x squared is a square number, a square variable, and 4 is also a perfect square. Therefore, I can write the first term as being the quantity 2x squared. The first term is a perfect square. So now I look at the last term. Is the last term a perfect square? Yes, it is. 3 squared equals 9. So now, before I can decide whether this is a perfect square trinomial, I need to look at this second term and ask if it follows the 2 times A times B pattern. Does it follow the 2 times 2x times 3 pattern? Well, 2 times 2x times 3 all multiplies out to 12x, but because there's a negative sign in front of this second term, we are following this second perfect square trinomial pattern where there's a subtraction sign in front of that second term. Therefore, we follow a subtraction sign inside the binomial that we square. So this is not going to be 2x plus 3, the quantity squared. It's going to be 2x minus 3, the quantity squared. Of course, if we're not totally sure, we can always do FOIL. We can always do the distributive property to multiply the values back out and check to make sure that we get back to our original polynomial. One super important thing to note here. Notice that there is no special pattern that gives you a squared plus b squared as your answer. This is not factorable using any special pattern. Sometimes after learning this special pattern, students think that they can do that a plus b, the quantity squared, somehow gives them a squared plus b squared. And that does not work out. So please do not fall into that trap. Perfect square trinomials have 3 terms. The only kind of special pattern with 2 terms that we've learned about is this difference of 2 squares pattern. All right. Let's look at how to solve a polynomial equation. We've learned how to solve these before. We use the zero product property, which just says if we have a multiplication problem, if a times b equals 0, then either a equals 0 or b equals 0. So following the rules that we've learned before, we have to start with a polynomial equal to 0. Well, here's my polynomial. It is equal to 0, so we're all set with step 1. If it didn't equal 0, we would just add or subtract from both sides of the equation until all of the variables, all of the constants are on one side of the equation and the other side is just 0. How to deal with fractions. If you've got a polynomial with fractions in it, the easiest thing to do is to just multiply both sides of the equation by the least common multiple. So here, there's no fraction. Here, there is a fraction with 3 in the denominator. There's a fraction with 9 in the denominator. Well, 9 is a multiple of 3 already. So if I just multiply both sides of the equation by 9, if I multiply times 9, then what I get on the right hand is just 0. 0 times any number is 0. But on this side, if I distribute that 9 onto each term, 9 times x squared is 9x squared. 9 times 2 divided by 3 is 6. So I've got 6 with my x. And then 9 times 1/9 is just 1. Now, this is a little easier for me to see that this is a perfect square trinomial. It follows the perfect square pattern because this is 3x squared. That's my a value. This is 1 squared, so 1 is my b value. And now when I check that center term, is it 2 times 3x times 1? Yes, it is. It does equal 6x. So this checks out. It's a perfect square trinomial. Therefore, I can write this, I can factor this as the pattern 3x plus 1, the quantity squared. Now, don't forget, this is equal to 0. We were working on factoring the left-hand side. We were working on a new way to write the left-hand side of the equation, but we still need to keep the right-hand side of the equation. It's still equal to 0. But now that I have a multiplication problem on the left-hand side, I can use my zero product property. One of the components of the multiplication problem have to be equal to 0. Otherwise, the expression could not be equal to 0. But here I actually have the same thing twice. It's 3x plus 1 times 3x plus 1. I only need to solve that once. So I'm going to say 3x plus 1 must be equal to 0. And so I solve for x by subtracting 1 from both sides. And then I need to divide both sides of the equation by 3. And I'm left with x equals negative 1/3. And that's my solution. Let's look at a real world example. We've talked before about how these types of polynomials with a square term on them are excellent for modeling free fall examples. And here we have a free fall example where a bird has picked something up and is now dropping it from a height. And here we have the equation y equals 81 minus 16t squared. That's the equation that models the height of the golf ball t seconds after it has been dropped. The question that we're trying to solve is after how many seconds does the ball hit the roof? If the roof isn't on the ground, of course, the roof is 32 feet higher up off the ground. We don't want to go all the way to y equals 0. We want to stop when y equals 32. So we can still use this same equation to calculate the height of the golf ball. It's just that we want to stop when y equals 32. We don't want to wait till the golf ball hits the ground. All right, so here, if we're going to follow our kind of step-by-step procedure for solving polynomial equations, the very first step is making sure that our polynomial is equal to 0. And this one isn't. So we need to subtract 32 from both sides of the equation because when you subtract a number from itself, you get 0. Resist the temptation here to divide because when you divide a number by itself, you get 1. And we don't want the number 1, we want the number 0. Let's write this in standard form. Let's write our t squared term first with positive 81 and we're subtracting 32. So if we write this out again, we have negative 16t squared plus 49. Now, polynomials are much easier to factor if our lead term is positive, not negative. So I don't want to have a negative 16 out front here. I want to have a positive 16. So all I'm going to do is I'm just going to multiply both sides by negative 1. Multiply by negative 1, multiply times negative 1. And I get that 0 equals 16t squared minus 49. I just flip the sign on each term in parentheses by distributing the negative 1. Now, this is a bit clearer to me that here I have a square term because 4t, the quantity squared, gives me 16t. So this is potentially my A value. 4t is potentially my A value, so long as this the rest of this follows a kind of square pattern of some sort. And then I'm subtracting, well, 49 is a square number. I've got 7 squared. So 7 is my B value. So if I have A squared minus B squared, that follows the difference of two squares pattern. And the difference of two squares pattern says that I factor by doing A plus B times A minus B. So 4t plus 7 times 4t minus 7. And this is all equal to 0. So I now use the zero product property to find out what the value of t is. Either 4t plus 7 equals 0, or 4t minus 7 equals 0. So solving for t, if I subtract 7 from both sides of the equation, I get that 4t equals negative 7. I divide by 4, and I get negative 1.75 as my time. Well, a negative time doesn't make sense. So this doesn't seem like a good answer to the question. Let's see what we get for the other possible value of t. Add 7 to both sides. We get 4t equals 7, divide both sides by 4, and I have that t equals positive 1.75 seconds. That is a much more sensible answer that does make sense in the context of a problem, and so that's the answer we go with. Even though mathematically this is a solution to the problem, it's not a solution that makes sense in the context of the problem. I hope this helped.